Hello. Ich mache das gerade auf die Maus. Du kannst ja schon mal.
Can we get a picture up?
6 und 7.
Oh, it is. Okay, cool.
Ich bin. Okay. Nee, warte mal, was ist denn das? Das sind nämlich Stümper. Der Empfänger in dieser Maus, der Sender meine ich. Das ist halt nicht dafür gedacht, dass man es in der Hand hält, weil da kommt nicht mehr genug raus. Ist okay. Ja, ja, ist okay. Ich mach's mit der Tastatur. Nee. Morning!
This is the Hitag talk. If you're not here for the Hitag talk, this is the time to stand up and go somewhere else. Technology is a wonderful thing. Karsten and Heinrich are going to tell us about Hitag. I'm going to get out of the way so they can do that. Thank you.
Hey, good morning or good afternoon. We are back again to break yet another RFID system, another proprietary RFID system that is in as widely of a high security use as the MIFA is. We broke a while ago, so this should be interesting. This time around, though, we want to talk more about the process, so to more enable you to do the same, since we get a little tired of breaking these things and explaining every single detail. We want you guys to do the same. So we'll throw at you a couple of techniques, how you can use your computer, not even any RFID equipment, just your computer and your sound card to sniff data and then throw at you a couple of tools that will allow you to break the cryptography. So this should be interesting. Let me introduce Henrik from the CCC in Berlin, ingenious RFID hacker, also pursuing his PhD at Humboldt University in Berlin at the moment. I'm Carsten, up until recently at the University of Virginia, at the moment mostly security consulting, trying to bridge the domains of academia, industry, and hacking, bring those closer together. The system we're going to look at today is the Hitag. We understand that it's used in car keys a lot. We don't actually know how widespread it is, but we'll find out in just a minute. And as I was saying, we want to teach you how to break this system as a generic process. So you should be able, after this talk, download some tools and get started hacking your own proprietary RFID system. There's plenty of them still around. We will talk about how to sniff data that is exchanged between an RFID tag and its reader, with, in this case, just a sound card and a little loop antenna. We'll then help you understand how to interpret these signals as bits and bytes, then further along the process, how to interpret these bits and bytes as messages being exchanged and what these messages actually mean. And in case that there are cryptographic, meaning encrypted, some authentication protocol, we'll show you some simple techniques how to break the encryption and how to break the entire system eventually. But first off, let's do a little experiment. How many of you are carrying a car key? Car keys, yes. How many of those cars are, say, less than 7 years old? Okay, can I have all of you come up here and just quickly swipe your car key over this reader so we can find out how widespread this technology is? Because honestly, we don't even know. We know we can break it. We don't know who's using it. So for those of you who do come up here, you'll see that Henrik is using a commercial RFID reader for this, just for reliability's sake. We could have been doing this with just a sound card that we'll be talking about later.
Even worse.
Okay, interesting.
Not high-tech, but this one is not high-tech, but it has it sends a data signal, and it's obviously even worse because it doesn't do any challenge response.
So we found something other than high-tech. So there's definitely the next project idea laying on the table here. What was the manufacturer of that? Volkswagen is using RFID, but not high-tech.
Okay, it doesn't respond. Probably not. This is keyless?
Yeah, it's keyless. You don't have a key. There is a key if you want to use it, but you just use it.
And
swipe just a little key. That should have it in it too, right?
No.
No?
How do you enable the ignition?
You just put this in the dashboard.
Okay, then it's probably a different protocol.
Different protocol. Press that to pick it up.
No, it's this is a higher range probably to open the door.
Okay.
That's probably not high-tech. High-tech
So
is more
BMW using RFID, just not high-tech. This is the newer keyless ones. Fancy. That looks good?
This is high-tech.
This is a car key? Seriously? What? This is Renault? Yeah. I take it? Okay, Renault.
Don't tell you where it is.
Well, we are not recording any data here, just for the record. All we are seeing is what's up on the screen here. We're not taking any logs.
I saw something just a moment ago. Yeah. The LED doesn't light up, but they're probably using the encryption. The reader doesn't know the key to the key, but it's responding and it gives us its UID.
Okay.
Okay, this is another one of the bad ones. You see there's a data signal. that is there regardless of whether the reader sends an inquiry or not. You just have to put that next to a RF source and it will respond.
So that is what then?
That's
Seat, yeah.
you can replay these, for example, with an iPod. That's what I did at the CC Congress 3 years ago. Yeah, this is.
So we are noting Seat, a subsidiary of
replayer.
Volkswagen, uses a different technology than Volkswagen, one that doesn't even use encryption, just for the record.
Okay, another high-tech one.
What manufacturer is that?
Opel.
Opel. Oh,
It's also using the
as
encryption.
if they don't have enough problems already.
It's also using the encryption, so it.
Opel is a subsidiary of General Motors, so chances are General Motors uses those two then.
Okay, this one doesn't respond at all. Not high-tech, I guess.
What was that? Mercedes? Mercedes not using it? Henrik?
Not using.
But something else in it, right?
No. Okay, this one doesn't respond either. Support?
Is it a door key?
Ford, yes or no?
Door of my phone?
No.
No. Well, Ford is using a Texas Instruments chip. That was hacked about 5 years ago.
Okay, it doesn't respond.
Could we ask that while they're doing this, could the audience please keep
It's not
the
high-tech,
sound level down so that we get a good recording of the talk, please? Thank you.
This one responds. It's high-tech and it's not. It is using the encryption.
Okay, so the first, where we're seeing the encryption.
No, they all use
Oh.
the encryption.
This is
Peugeot.
Peugeot, another French one.
Citroën.
Okay, I saw something. Yeah, it's high-tech. It's responding and it's also using the encryption.
What manufacturer is that? What Citroën. Oh wow, all the French ones then.
Yeah, it's again the same. High-tech, encryption.
What are we looking at there? Opel again.
This is again one of the bad ones. It's just sending its ID out without any inquiry.
What was that? Audi? Audi. So yet another subsidiary of Volkswagen not using any encryption.
Not responding, not high-tech.
That was an access control card, right?
Okay, I think we had that before.
Something advanced,
Uh-huh.
Yeah, high-tech encryption.
Yet another Renault. Yeah.
Okay, that's one of the bad ones. That's again one that simply sends its ID. You can watch my talk 3 years ago at the Congress.
Okay, so just for the record, we have all the French and one German car manufacturer. Chances are General Motors uses it too, though. We know that Ford hasn't been using it since they use something worse, and apparently Volkswagen and its subsidiaries use something yet worse than that, where there isn't even anything to be broken. Okay, let's move ahead with Henrik telling you how to sniff the data, how to interpret the data, and how to document a protocol nicely. And then we will get back to the crypto and how to actually break it.
Okay, the first thing I did was to Google for information, and I found 2 data sheets that some manufacturer left on their website unprotected, which describe, the one describes Hitag 2, which we are looking at here, and the other describes Hitag S. Apparently there are 3 Hitag types, 1, S, and 2, where Hitag S seems to be an update of Hitag 1, and Hitag 2 is almost completely different. They are all using the same encryption, I think, at least from what I can gather from the data sheets. I had only Hitag 2 tags to play with, so that's what I'll be focusing on. The Hitag S is available in different memory sizes. This information is mostly all gathered from the data sheet. They have a simple ID-based tag with only 32-bit fixed memory. They have 265-bit tag and a 2048-bit tag. They are all organized in the same way, different pages. Each page has 4 bytes of memory, and the first page always contains the UID. If they are using the encryption, they are storing the 48-bit key in some of the first sectors, or they have a different mode where they only use a password that's also stored there. The radio protocol that's described, this picture is actually from the datasheet, that's described in the datasheet, is they claim the operating frequency is 100 to 150 kilohertz, where they are usually operating at 125 kilohertz. That's also what this reader uses. The data transmission from reader to tag is simple on-off keying, 100% amplitude shift keying. And their data format, their coding is pulse length. That means they are switching off the field for short amounts of time. And the time between two field off states encodes the data. So this is a 0-bit, this is another 0-bit, that's a 1-bit, that's a 1-bit. What you can see here is that the 1-bits take longer than the 0-bits, so the data rate is actually data dependent, which is kind of crazy. The transmission from tag to reader is load modulation, as everybody uses, and the Hitag S datasheet specifies quite a lot of different modulation and coding schemes. They have 3 coding schemes and 3 different data rates. But since I haven't seen any of these tags, I'm not sure what they are actually using. The data rate is 5.2 kilobits on average from reader to tag, and from tag to reader is dependent on what you have configured. There are also tag talks first modes, that's what they call them, where you can program the tag with data content and set a configuration bytes so that they will behave just as if they were stupid tags. We have seen some of these car keys where the tag simply sends a continuous stream of data without any transmission from the reader, only the field from the reader, and then it will start transmitting. That's also what some access control cards use, for example, the NADAP card that I demonstrated at the Congress several years ago. These are really easy to clone because you just need to record the signal and then can replay it with a simple circuit and any audio source I've used in iPod. And they have these modes in there for backwards compatibility if you have some of these old systems. The datasheet specifies quite a lot of different commands, and the protocol seems to be organically grown. You have this UID request command, which is 5 bits. The Hitag S actually has an anti-collision procedure where the Hitag 2 doesn't. And I really like their select procedure. They have one select command that is basically the command and the UID of the card you want to select. And they have a select but go to quiet mode command. That's the same command, but with one additional 0-bit inserted. So it's not byte-aligned or anything, organically grown. Their authentication in Hitag S is similar to what we are seeing in a short moment on Hitag 2. The reader sends a 32-bit random number, a nonce, and calculates based on this random number the UID of the tag and its secret key, an authentication token that's transmitting after the nonce. After which the tag will use the cipher state and respond with its password in encrypted form. What you can see here especially is that there's no randomness supplied by the tag, so you can replay that easily. Yeah, Hitag 2, which is what we've looked at, is only available in 256-bit of memory, which means they have 8 pages of 4 byte each. The first page again stores the UID. Page 3 has configuration and tag password. And the last 4 pages are freely configurable for user data. And the remaining pages are storing secret data, which is either the key or the password. Through the configuration, you can again select one of 2 different modulation schemes, biphase or Manchester. They are set to Manchester by default, and that's what I'm using. They have two Tag Talks first mode for emulating older tags, which are listed here, so that you can upgrade your system or just buy their tags instead of the older ones. And the most interesting part is whether you have crypto or password mode. There's one bit that selects the mode. They are in password mode by default, and will go to, you can set the bit and then it's in crypto mode. In password mode, they have a cute thing that's more like mutual authentication. They do that by the reader sending one password. The reader sends a 4-byte password, and the tag responds with a 3-byte password. So they are mutually authenticated, kind of. It's obviously easy to sniff and emulate and replayable. There's also the other mode, the crypto mode, where they use the protocol I explained before. The reader sends a 32-bit nonce, and immediately after that a 32-bit authentication token, to which the tag responds with its configuration and its own password. So the tag doesn't do authentication through challenge response, but just by responding with its password in encrypted form. And there is no randomness from the tag involved at all. All further communication after that is encrypted, which is different from Hitag S. In Hitag S, only the authentication is encrypted, and afterwards everything is in the clear again. The activation procedure, this is information I reverse engineered by sniffing the protocol. I will show you that in a moment. The activation procedure is again a 5-bit command to get the UID, then the tag responds with its UID, which is simply sending out the contents of page 0. Then the reader responds with its reader password, which are the contents of page 1, and the tag responds with its configuration and tag password, which are the contents of page 3. In crypto mode, starts with the same 5-bit command, so you again transmits the UID, so you have to, if you are the reader, you have to know whether the tag is in crypto or password mode, otherwise you can't do that properly. And then the reader transmits its random number and authentication token, to which the tag responds by encrypted configuration and password. Afterwards, all further communication is encrypted through the cipher string. Yeah, their read commands are again not byte aligned or anything. It's just 2-bit command, 3-bit page number, and then the same but inverted 2-bit command, 3-bit page number. That's the read command. The write command is similar but with a different command code. And for write, the tag repeats the command code in order to confirm that it's really able to write and willing to accept the data, and afterwards the reader sends its content that it wants to write. Sniffing, that's what we did right at the beginning. As I said, they are using a 125 kilohertz carrier, and they have a rather low data rate, which means that the maximal frequency that's used in the modulation is 16 kilohertz, which is well within the audio range and well within the capabilities of any sound card. So I can use a simple diode detector radio. That's what they used in the 20s or last century for simple, it's a very simple radio, type of radio that you can use to receive amplitude modulated data. It's just one diode and a tuned antenna. So it's just 3 parts in this complete circuit that you are seeing here. It's connected to an iPod because that's the old image I used 3 years ago. Now I've just connected it to my sound card. And then I'm either using Bautline, which is a nice tool for audio visualization and recording and playing with it, or a couple of lines of C for proper decoding. That's a screenshot of my Bautline screen. I can show that in live now. And as you can see, the reader, every 1 second, it interrogates it enables its fields and sends the get UID command. If I move the reader antenna away from my sniffing antenna. You see, you don't see anything anymore, and if I put my reader antenna on there, it's receiving data. And if I stop the recording for a moment, I can actually look at the waveform.
Just for clarity, so all you need to have to sniff data that's exchanged, say, between your car and your key is this piece of cardboard with a little antenna on it, and a computer with a sound card. There's no RFID equipment involved.
You don't actually need a cardboard piece, but...
the cardboard is optional, yes.
Okay, this is the data that the reader transmits. I'm not sure why it's so dirty now. Normally it's more clear. Unfortunately, I can't zoom in any. Okay. So this is, as I said before, these are 1 bit, that's a 1 bit, and that's a 1 bit. They are longer than the 0 bits. That's a 0, another 0, and another 0. So that's 1, 1, 0, 0, 0. That's the get UID command I explained before. And if I put the tag in the vicinity of the reader, you can see what we saw before. Here's the command from the reader, and that's the what the tag responds. It's Manchester encoded, starts with a starter frame marker of 5 ones, and then comes the UID. After which the reader, as I explained before, sends its reader password in the clear, and
the tool we're using here, by the way, is called Botline.
yeah.
It's a free tool, unfortunately not open source. If you are the developer of this, or you know the developer, please ask them to open source this. We want to extend it. We want to make it a lot better. It's an ingenious tool as is, but a few things are missing to make it a real powerful RFID sniffer.
Okay.
So we want the sources of this, please.
A moment ago, I put the other tag on here. This tag is configured for crypto mode, and this tag is configured for password mode, so it didn't respond. What we see here is, again, the get UID command, the UID of the tag, then the reader sends its password, and the tag responds with its password, all in the clear. And then I have the couple of lines C I mentioned before. I have recorded a transaction, or actually I can do it live. Let's see whether this works. So I've just recorded an audio file, foo. See whether that works. Yeah. What you see is this is live, was live, recorded live. This is a 5-bit get UID command. That's the UID of the tag you see here. It's 11303335. I don't know why they reversed it. That's the reader password. It's the default password of Micre, because it's the company was Micron, and they have used the first 4 bytes of the name for the default password. And then the tag responds with its configuration byte, which is 06, means it's configured for password mode, AA, and then HT for Hitag. These are the default passwords. And I have another pre-recorded sample.
And this protocol is completely documented in a PDF that's floating around the internet.
This protocol is not documented. I've reverse engineered that.
Okay, never mind. Well, there is a 150-page document. I thought everything must be in there if it's 150 pages.
No, they don't have the commands in there. They only have the... Oh, okay, they have the commands in there, but for the Hitag S tag. The Hitag 2 is not in that PDF, and I haven't found a PDF that describes the Hitag 2. This is another sample which I recorded previously. That's the crypto tag. It's again 11000 get UID, UID of the tag. You see that's the other UID 11703DA4, and this is what we will be talking about in a moment. This is the random number of the reader and the authentication token that the reader uses, and afterwards everything is encrypted. You don't see, here is the tag password, you don't see it anymore. This is read sector 0, which normally would be 11000, and it's not in there anymore. it's encrypted, contents of sector 0, and so on. Okay. Sniffing, yeah. The cipher. Look what we found on the net. Apparently someone named IC Wheeler had already reverse engineered or somehow obtained the cipher and put it on a web page, and I've confirmed through my sniffs that's actually the cipher that's being used.
Now, somehow IC Wiener told us this is coming from a firmware dump. So they extracted the firmware from one of these readers and just found a cipher in there. They didn't actually reverse engineer the alpha detect or any of that like we did with the MyFair. It's a very similar cipher though. So there's often different avenues of getting to a cipher like this. But just for the record, it's always possible. Don't try to hide ciphers.
Yeah, the cipher is similar, but the initialization procedure is much simpler, as you can see. They are loading the key and the serial number in there, and the authentication token, which we saw before, is just the first 32 bits of key stream, but inverted. With this, I'll get to Carsten's part of the talk.
Yeah, well, let's talk about how to actually break this now. Since this is cryptographic, this is using a not a large, but not a super small key. So there's definitely several ways we could be attacking this in. Just 1 second. And since this is a card used in modest to high security applications, including governmental access control cards in Germany, for instance, but also car keys, as we've seen. Since it is used in these applications, one would consider this a valuable target for an attacker and one that should be protected definitely below the bare minimum of, say, a micropayment card, as the MyFair is in most instances. I would imagine that an attacker would put down something 5 digits to break even into one car. If there was a process or an attack one could set up for less than that to break one car, or for considerably more than that to break into as many cars as you want, an attacker is going to put down that money. So the attacker cost that this should exceed is definitely 6 digits. There's a number of attacks you could be using against this system, all of which are definitely below 6 digits. The most expensive one and the most straightforward one is a brute force attack, in which you try every possible key. There's only 2 to the 48 keys, and it will take you a couple of weeks to months on the computer to try all of these. It will be much faster if you invested some money into FPGA resources. So with just a small FPGA cluster, you can be breaking these car keys, say, in a minute if you wanted to. Definitely worth an investment if you're in the business of stealing cars, I take it. More interesting, though, are attacks that exploit more the protocol or even the structure of this cipher. More interesting, certainly from an academic point of view, because we point out weaknesses beyond small key size. Everybody knows this is a weakness that we can learn from. But also more interesting from the attacker, of course, because these attacks are even cheaper than investing a few $1,000s into FPGAs. The one generic attack that is possible against this protocol is a rainbow table precomputation, in which you compute a code book, basically a reverse mapping from what comes out of the cipher that you see and to what key went into it in the first place. There will be a talk today at 5 that goes a little deeper into this topic, so I won't touch on it too much now. One much more interesting attack, though, that attacks the cipher itself is what we call algebraic attacks. An attack that exploits the nature of the cipher and tries to reverse it where this should not be possible. Apologies if the next couple of slides are a little bit technical and theoretical. We have been asked over and over, though, how we actually go about breaking crypto once we have it. And I want to answer this once and for all. And I want to answer it in what I think is the best possible way by giving you a tool so you can go through this process again without understanding too much about the cryptography. So I'll be giving you just enough background so you appreciate and understand how to use this tool. And then whenever you come across a cipher, you can break it. I'll also be explaining you how to spot weak cryptography, which is important if you do your own disassembling, for instance. So one step back, though. How do you generally break a cipher? Of course, a cipher is designed as a mathematical function that you can go in one direction, say from plain text to an encrypted text, but never go back unless you have some secret information, a secret key. So it's a street you can really go only in one direction in. The way this is tried to be achieved in cryptography is through building up complexity in the way from the inputs, the secret key, to the outputs, what, say, an attacker would actually see, and try to pile up as much complexity as possible. I'll be explaining or defining a little bit more closely what complexity in this context means. But just for your mental note, trying to throw as much mathematical complexity at it makes it more one way. Now, of course, there's a trade-off between doing that and having it really cheap in hardware, for instance. So designers will try to find the gold middle way where it's still very cheap in hardware and perhaps software, yet piling up enough complexity for this to never be reversed. Now, I'll be introducing a tool here that can actually reverse a whole group of ciphers. So this isn't a tool specific to Hitag or any one cipher, but rather to a whole group of low complexity ciphers. Just for the computer science geeks in the room, we're really talking about a P-NP complete problem here, where if you're NP complete, you're definitely too expensive. When you're P, you're definitely too cheap to break. So this is the gold middle you need to strike. And introducing yet another way of describing this. So we were saying linear, we were saying non-complex complex, and in cryptography we would say linear and nonlinear. This will be the last concept I'm introducing here, then it's more fun again. A linear function is, say, the XOR of terms. If you have 10 things to play with, the longest possible XOR you can be compiling is of length 10. If you XOR any of the 10 in it again, it will cancel out at least one of them. So if you stay linear and you have n things to play with, you'll never get beyond length 10, or n in this case. Whereas if you use other functions, and, or, and so forth, and you're combining, say, your A and B term into an A and B, and then XOR those, you can get exponential. So with your n things to play with, you can go up to 2 to the n lengths. And of course, I'm talking about the description of the cipher in the most generic form, right? Sorry if this was too theoretical, but it needs to be said once. So what we're doing here is describing ciphers in generic ways, describing the mapping from the secret key to the output in a way that the computer can understand and perhaps reverse. We're saying that linear is bad and nonlinear is good. Surprisingly so, though, all stream ciphers, even new ones that I come across in hardware, use what I call a linear feedback shift register. I'm sure you have seen those before as well if you've ever looked into cryptography. Those are very handy building blocks with nice mathematical properties, only they are completely linear. What these are doing is XORing numbers. So if this is of length n, the equations that come out of it are at most n terms, XOR terms. Is this understood by everybody? That if you only do XOR, you can't ever exceed a certain number because eventually things will cancel out again, right? Now, Hitag, of course, uses this too, being a stream cipher and being a proprietary stream cipher. How could they not? So Hitag is highly vulnerable against reversing attacks. This, in fact, is the Hitag cipher. It does have a fairly large linear feedback shift register. It only has one, though. So there's 48 bits in this state down here, and they're XORed over and over again with themselves. leading to XOR terms in here in each of these cells of length at most 48, right? What's being done then is kind of smart. It's fed through a filter function that is very highly nonlinear, degree 20. So this would be hard to break if there were to feedback whatever comes out of this filter function into this state, so that once it goes around and round, it gets more and more and more complex. It piles up nonlinearity. Unfortunately, or fortunately for us, they forgot the one wire that would connect this back to here. And they don't build up this complexity, even though all the building blocks are here already. Alternatively, of course, they could just introduce some nonlinearity in the feedback. So instead of using a linear feedback shift register as this one could very well replace one of these XORs with an AND or with an OR, adding virtually no cost to the hardware, not changing any of the mathematical properties, yet adding huge complexity in every round. This will go around here dozens of times, and in each round will accumulate complexity. Well, this is not being done, fortunately for us, so we have a cipher here that's easily described with very low degree equations. On this slide, the only number that's important is the 4 down here. Everything else is for reference. So we can describe this entire cipher with terms of degree 4 or less. Where really, if we have something 48 bits, we want to have terms up to 48, right? Otherwise, we waste the potential of the key size. Well, suffice it to say, this is at most degree 4, so we can easily break it. Everything up to degree 7 is almost trivial. Now let's get back to this tool I was promising you. There's a whole group of tools called the satisfiability solvers. They're used in CAD design, they're used in electrical circuit optimizations, they're used in a whole bunch of design areas. Now, we want to use those in a destructive area, meaning breaking crypto. And we did take one of these tools and modified it to be able to break ciphers. The one thing we had to add to the tool, though, was an understanding of the XOR function. So I was saying that the linear feedback shift register gives us modestly sized XOR strings. Set solvers, as they're designed, don't understand XOR. And in fact, XOR isn't really used that much outside of cryptography anyhow. So what we did is take this standard tool from say, electrical circuit design and add this one piece of mathematical insight into it. And what we have is a general purpose breaking small ciphers tool that has been released under GPL. So there will be a link on the last page linking to Mate's source, my co-author in this case. And this tool can now break ciphers like Hitag. This is the internal representation in the tool of the Hitag cipher. So when I was talking about complexity initially, that you want to pile up as much complexity as possible, of course it wouldn't ever fit on one page describing it. This cipher does, so this gives you a good intuition already that this is too weak. And in fact, if you look at any cipher that you find in, say, a software disassembly, and it only uses XORs and maybe a few mapping tables, you can probably put it down on one page, and then you can also break it using these tools. It takes about 6 hours on a PC to break this. We might move this to an FPGA to make it faster, but really, if you can steal one car every 6 hours, selling them will be your bottleneck probably. So this is as low of a security as it gets. Just before wrapping up, and let me move to the original picture here. This is not really bright enough. Just to give you an idea of how the set solver is actually breaking the cipher. It is executing a brute force attack, really. So it's trying every possible key, only it does it in a smart way where if it already knows that certain keys are not possible, it won't even ever touch them, but rather try the most likely ones first, and then easily hit the right key within the first couple of guesses. If you were to sketch out a brute force search of a 2 to the 48 cipher, that's pushing 1 trillion different keys. Well, I did draw here what the set solver is doing. And while these boxes are very small here, there's definitely not a trillion of them, right? There's a few thousand on this page. And that's all the keys that the set solver needs to try. So there's each of these boxes is one attempt of finding the right key, and down here it did find the right key. So compare this to a tree of a trillion nodes, and you know how much smarter the set solver is about brute forcing. The beauty of this approach, however, is that it is as generic as brute forcing. So there's no mathematical function that you can't solve using this way. It's just a matter of waiting for it to find the best possible key. And that, again, depends on your complexity, which, again, depends on your nonlinearity. So, which brings us back to why this cipher is so flawed. It uses a linear feedback shift register. To wrap up briefly, we want you, of course, to get involved in this and to break RFID systems too. I think we've shown that it's pretty easy to sniff data, at least in low frequency, in the low frequency domain, that it's somewhat straightforward to find what the sniff data means, since the protocols are very easy. The hardware in the RFID is very easy. And then I've given you this tool that you can use to then break a cipher if there even exists a cipher. And with all of that, we hope we open up the hardware hacking, the RFID hacking domain a little further. And I hope we have some time left for questions now. And I'd like to engage you in a little discussion on whether you think...
We have exactly 4 minutes left for questions.
Okay, cool. We have 4 minutes, so a couple of questions. But first of all, thank you very much. The tool can be downloaded here, and please send us emails if not all the questions are answered here. Thank you. Are there any questions?
The first one is over there. Michael? Oh?
Would it be possible to extend the set to also support rotate, shift?
Well, it already does. The question is, can we extend the set solver to support shifts and rotates? Well, the way we are doing this is for every shift, and I know you can't really see what's in these boxes, for every shift we introduce a couple new boxes in here. So this is the mapping from the input bits to the output bits, and the more shifting is happening in between, the more boxes you'll get, but it's already supported. Of course, a linear feedback shift register is nothing but shifts and XORs.
Yeah, I better say
Data-dependent shifts? A data-dependent shift is a nonlinear function. And of course, it is supported. You can map this into a set solver. It will become very hard to solve it, though. So an A51 cipher, for instance, that has data-dependent shifts, is not easy to break with a set solver, right? But it is already supported. There's nothing you need to add. The way I'm looking at set solvers is they are a metric for how strong a cipher is. So they pretty much measure how nonlinear it is. And data-dependent shifts are very nonlinear. So what you'll get from your set solver is the result, this is very hard to break. Any more questions? In the back?
Have you considered to use a binary decision diagram for your set solver?
Sorry, I didn't catch that.
Have you considered to use binary decision diagram for your set solver?
Using what?
Binary BDD.
Binary
decision diagram.
Binary decision tree.
Yeah, the principle is is that they compress your logical formula. Okay. And if it's simple enough, you will. I think it will improve your.
We've been doing something not under this name, but we've been running Gaussian elimination on this to simplify the terms. Yes, and there will be an extension coming out to this crypto mini set pretty soon, whenever we finish the paper, and that will add many more entrance filters. So if instead of throwing this at the set solver, we'll first pass this through a bunch of layers and simplify it. But it will take off 1 or 2 orders of complexity. Still, it will still have the same distinguisher between breakable because it's linear, non-breakable because it's non-linear, right? But yeah, we're still working on it.
We can talk about it.
Thanks for the question, though.
There's one question in the back. Can we have a microphone there?
What's that?
Where is the RFID village? Please put it in. If you, I guess you are at the RFID village, aren't you? Yes.
I can't really understand that. Let me come over there. RFID? No. No, we're not at the RFID village. Sorry. But we are around. If you have questions, just find us. There's a question down there.
What's in between the antenna and the audio in?
What's in between the antenna and the audio in, Henrik?
It's very hard to understand with the PA system.
Beschreib mal deine Antenne. Was für Komponenten hat deine Antenne?
Mein was?
Deine Antenne. Beschreib mal dein Papier.
Yeah, this is the receiver. It's very simple. It's just a loop of copper wire and capacitor to tune it. And then there is a simple diode in series that's used as the amplitude modulation detector. With this you will get the basic signal, the 125 kilohertz, the carrier, modulated by the signal from both reader and tag. But because the bandwidth of the sound card doesn't extend up to 125 kilohertz, it's a cheap-ass low-pass filter that will only let through the data signal. And I've also a modulator that's the same principle, a spool of copper wire and capacitor, and then there are 2 additional parts, that's a resistor and a transistor, that are used for load modulation. So I can also put in a data signal through a sound card output. In principle, it should be possible to build a modulator with just the sound card and these 2 things. The only problem is that the Hitag protocol asks for a latency from request to response of about 2 milliseconds, and it's kind of hard to do with the sound card. I've built an emulator with the Proxmark hardware that Bill talked about yesterday, so I did have an emulator. Somehow I broke it yesterday, so I couldn't demonstrate it. But I have a completely working Hitag 2 emulator that also does the crypto and responds to all the commands that I described. So if we have the tag data, we can emulate it if I can fix this thing.
Do you want to come up to the mic?
So it sounds like adding XOR to the SAT solver is similar to, say, adding like the theory of bit fields to an SMT solver. Was there some reason you didn't just use an off-the-shelf SMT solver instead?
Well, an SMT solver doesn't exactly do what we want to do, but yeah, we have been looking into SMT solvers. So it seemed easier to kind of capture what's needed for crypto from the SAT solver domain than from the SMT solver domain. If somebody came up with a mix of those 2, balancing for each part how to solve it best, that would be optimal, but we haven't found an expert in SMT solving yet, honestly, and SAT solving was much easier to learn. Thanks for the question, though. So if there's no more questions, thank you very much. Please consider Hitag broken for all future applications, and talk to your local car manufacturer that they please phase this technology out as soon as possible. I was told this takes about 8 years for car manufacturers to move to new technology. So for the next 8 years, have fun breaking Hitag car keys. Cheers.